Hi everyone, this is Mrs. GA, and today we're going to talk about polar forms of complex numbers. So remember, a complex number is a number that has an imaginary portion. So it's in the form of a plus bi, and we call a the real part of the complex number, and then bi is the imaginary part of the complex number. So it is possible to graph complex numbers. However, we do need to graph them on an imaginary axis. So instead of being an xy axis, the horizontal axis represents the real number, and the vertical axis represents the imaginary number. So for example, if you were to plot the complex number 2 plus 3i, you go 2 on the real number, 3i on the imaginary number, and where they intersect is your coordinate. So another example, maybe if we wanted to graph -2 minus I, again we go -2 on the real axis, -I on the imaginary axis, and our coordinate would be right here. Okay, so it's very similar to graphing on a rectangular Cartesian axis, except again this represents the real portion and this represents the imaginary portion. Okay, so one important feature of complex numbers is what's called the modulus, or sometimes it's also called the absolute value. So we represent the modulus by what looks like absolute value of z, so this stands for the modulus, and it can simply be found by doing the square root, the positive square root of a squared plus b squared, where a again is the real number and b is the coefficient of your imaginary number. So let's talk about what this really is. So remember, this distance from here is a, and this distance is b. So if you're doing the square root of a squared plus b squared, that's just Pythagorean theorem helping us find the hypotenuse of this right triangle made when you connect the origin to your point. So maybe this is very similar to like the r value of a polar coordinate. So it's the distance from the center to your coordinate. And again, it should always be positive. So let's practice finding the moduli of these two complex numbers. Again, it's really easy to do. It's just Pythagorean theorem. So for that first one, it's going to be the positive square root of 3 squared plus 4 squared, which we know this is like a 3, 4, 5 triangle. It should be 5. And that's all there is to it. All right, let's do one more. So again, the modulus is going to be the positive square root of 8 squared plus -5 squared. So this just becomes the square root of 89. And that's really all there is to it, to finding the modulus. So the reason why we need to know how to find the modulus is it's going to come up on the next slide when we learn how to write a complex number in polar form. Okay, so again, here's the complex form of a number, and any complex number or form can be rewritten in polar form using this formula. So we say z equals r times cosine of theta plus I sine theta. So here, notice this z is not the same as the modulus. The modulus is represented by the absolute value of z symbol. So this is just the way we denote the polar form equals. So this r value right here is actually the modulus. So you find the modulus and that value goes here. And then theta you can find using the trig ratio tangent. So we can say tangent of theta is b over a. And again, that helps us find here, and then we'll need to use arc tangent to help us actually solve for theta. And just so you know, theta is called the argument of your answer. I do want to point out that you need to make sure that your angle is in the correct coordinate. So for example, if you are working with a complex number that is down here in quadrant 3, this is your A value, this is your B value. So for theta, this would be like the reference angle of our larger angle. So we could still set up the equation. We would say tangent of theta is B over A. So theta equals the arctangent of B over A. However, remember, we're just solving for this tiny little sliver, and we want the entire sliver. So whatever we get here from the arctangent, which will be an acute number, we do need to make sure we add 180 or pi to make sure it ends up in the correct quadrant. So just be careful what your calculator or what your arctangent expression tells you is not always the angle you're actually looking for. All right, so let's practice writing these complex numbers in polar forms. We're going to do each one together. So when you're doing this, I recommend starting just by plotting your point, just to make sure you know which quadrant you're working in, and it will help you later on when you're working with the argument. So again, this is 1, and this is 1, and this would be the angle. So again, let's start by finding that r value. So remember, the r value is just the modulus, so it's the positive square root of 1 squared plus 1 squared. So in this case, r is going to be the square root of 2. And then to find our argument, which remember is that angle, theta, we would say tangent of theta equals 1 over 1. So theta is the arctangent of 1, which is pi over 4. And then from here, all we need to do is substitute it into that polar form. So we do z equals r, which is root 2, times cosine of theta, pi over 4, plus I times the sine of theta. And this is the polar form of 1 plus I. Okay, let's try this next one. Again, I recommend just really quickly sketching out where this is. So -1 positive root 3 would be right here in quadrant 2. And it's telling us that this is -1 and that this distance is root 3. So let's start by finding our r value. So again, it's just the modulus. So it's the positive square root of root 3 squared plus 1 squared. So here we end up with the square root of 4, which is 2. And then we do need to find this angle, theta. So we can start by using the reference angle in here, and we can use tangent. So we could do the tangent of our reference angle, theta prime, is root 3 over -1. So here we know that the arctangent of negative root 3, so that tells us that our reference angle would be negative pi over 3. But again, we want this angle, so we need to make sure that we're adjusting it to place it into quadrant 2. So again, if this distance is pi over 3, we know that this distance should be 2 pi over 3. So theta is 2 pi over 3. And then again, we just use that the polar form to write our equation. So z equals our r value, which is 2, times the cosine of 2 pi over 3, plus I times the sine of 2 pi over 3. Okay, let's now try part C. So here for part C, we have a negative A value and a negative B value. So we are down here in quadrant 3. So this is -4 root 3. This is -4. Let's find R, which is the modulus. So -4 squared plus -4 root 3 squared. So here we get square root of 64, which is 8. And then we do want to find, remember, this total angle, but we can start by finding this little reference angle. So we can say tangent of theta prime equals -4 over -4 root 3. So this becomes tangent of theta prime equals root 3 over 3. So here we know that theta prime is pi over 6, but again, this is pi over 6. We want this entire angle, so our argument, theta, is going to be 7 pi over 6. And now we just substitute those two things into our polar form. So z equals r, which is 8, times the cosine of 7 pi over 6, plus I times the sine of 7 pi over 6. Okay, we're going to do one more together. So here, again, let's plot it just so we know what quadrant we're in. +3, +4, so we're in quadrant 1. Let's find our r value, which is the modulus. So it's the positive square root of 3 squared plus 4 squared. So r is going to be square root of 25, which is 5. And now let's find theta. So the tangent of theta is 4 over 3. So you'll notice that this is not a unit circle angle, but we can use our calculator to give us a decimal approximation for the arctangent of 4 over 3. So for theta, we get approximately 53.1 degrees. So here we can say z equals r, which is 5, times the cosine of 53.1 degrees, plus I times the sine of 53.1 degrees. And there you have it. Okay, so that is all for today's video. Thank you so much for watching.